Hello, and welcome to my session on LLMs, large language models, which is all around the world right now. But before we dive into LLMs, let's look at what is generative AI and let's put it on a map as to where these LLMs reside. We all know about AI. So, if this is the whole landscape of AI, which is artificial intelligence, a subset of this is what is generative AI or Gen AI. And then there is a subset of this Gen AI, which is the large language models, LLMs. Now, again, there are different architecture types within LLM, and one of them is the very famous GPT. Basically, that is a transformer architecture. It's not GPT, but since this is a widely used term, that's why I have put it here. Now, what is a GPT? Again, you all must be knowing, but I'll still write it down here. So the G here stands for generative. The P here stands for pre-trained, and the T here stands for the transformer architecture. So this is what GPT stands for. Now, the other architecture types here in the LLMs are GANs, VAEs, RNNs, and there are several others. And there will be a video that I'll be making on all the different types of LLMs and how they are being used. But in this video, we'll be focusing on the transformer architecture. Okay, let's take an analogy and understand the difference between AI and Gen AI. So AI is like a captain of a commercial ship who takes the ship into the sea and follows the navigator and reaches from one place to the other. Gen AI at the same place is something different. This is something like a sea explorer who ventures into the unknown areas of the sea, and it encounters a lot of things. It uses its expertise to navigate through all of them. So they are not following a specific set of rules. What AI was doing is following a specific set of rules. So, so things like if a security guard is standing in front of your clubhouse, that is like AI. It will say, okay, you are allowed to go in or you are not allowed to go in, right? This is a spam or this is not a spam. This is a cat and this is a dog and this is a wolf. So those kind of things that works on a programmed and a very rule-based thing, those were the generative AI. Those were the AI, the traditional AI. In generative AI, you see that it mimics human intelligence. So you can ask it to write a story and it won't repeat a story that it has learned. You ask it for a new story, you ask it to write a story of a flying elephant in the deserts, and it will create a story and give it to you. It can compose music, it can write books, articles, and you can even have a discussion with some of the Gen AI models uh, where they can role play. It can play the role of a lawyer, a security analyst, and different role plays. And it does all that based on how it has been trained, but it doesn't repeat that. It creates original content, new content, and that is the gen part of this, the generative part of this. Now we'll be talking about the different components of an LLM. So let me erase this and let's jump into the LLMs, the components of LLMs. There are four components of LLMs. So this is our LLM. One part I would say is the architecture. And we will be talking about the transformer architecture for most of the um, video. The other thing that you all have heard of is tokens. Tokens are the inputs when we are interacting with the LLMs. The third thing is parameters. I don't know if this will be visible. Let me write it here. Parameters. And the last one is the context window. So this is context window. And we'll be looking at each of these in details. And I will also be walking you through some of the OpenAI APIs and some very easy ways to actually try hands-on and see what these things are. So what we'll be doing is to understand this whole the way LLMs work. Let's look at a very basic neural network architecture, because that is what ultimately powers all these. Now, in the neural network looks something like this. So you have an input layer, you have some hidden layers. It can be any. In fact, in GPT-3, there are 96 hidden layers. We'll again talk about those numbers at a later point. I don't know again if this part is visible. So this is the input layer, right? Let me write it here. So this is the input layer. These are the hidden layers. Let me keep it to just two for simplicity. So these are hidden layers. And then we have an output layer. Oh, sorry, I have to erase this. So this is the output layer. Each layer consists of, so each layer consists of nodes. So these are the nodes here. And even the hidden layers will have nodes. Say this layer has four, this has four nodes, and there is one output node. And then these are connected. So neural networks are connected networks. They are something similar to our brains, where the neurons connect our brain cells. Similarly, neurons connect these nodes. So this is one node, and this is connected to all or many other nodes in this way. And each of these connections have some weight tied to it. I can take example of a number, or I'll just write W1, W2, W3, W4. So this is the relation. So this node is connected to this with weight 1, W1, W2, W3, W4. Okay? And similarly, all other nodes will be connected to a lot of this, making it a really messy kind of a very dense neural network. More dense it is, the better it is at performing like humans. I will not make that whole all that connections, because I want to explain something. And that is, how do we calculate the number of parameters? Now, in the actual neural networks, this hidden layer is like too many. But in this one, we are taking it to only two. In GPT-3, as I mentioned, there are 96 hidden layers. Okay, and the number of nodes is also enormous. Now let's look at how to calculate the number of parameters. So to calculate the number of parameters, what we will do is, we will look at all the weights. How many weights are there? So how many weights are there? Number of weights. So number of weights is 1, 2, 3, and 4. There are 4 different weights. We are calculating the number of parameters if only this was our neural network. So number of weights is 4. And then we have something called bias, which is equal to the number of nodes here. Right? So the bias in this layer is 4. So what we do is, for calculating the number of parameters, we say number of weights, and then we add bias to that, right? Now, this is what will be the number of parameters if my neural network had just one node at the input and 4 nodes in the hidden layer. Now let's make it a little complicated. This input layer had 3 different nodes, and they are also connected. And then we also have this guy here, and this is also connected. Right? So each of these nodes have these 4 weights, these 4 lines, these edges, those are the weights. So in total, if you look at, now we have 3 nodes in the input layer and 4 nodes here, and all of these are connected. So basically this becomes 4 for the first one, 4 for the second one, and 4 for the third one. So this becomes 4 into 3. So 3 nodes into 4 number of weights. So now, if this was my neural network, my number of parameters would be 12 plus 4, that will be 16. Now this is only if we have such a small thing. And then the same thing will be replicated here and then replicated here, right? And imagine when you have so many hidden layers with so many nodes. Just imagine how many parameters are there. And more the number of parameters, more it can act like a human brain, because that becomes very dense, very rich. Now we will be looking at the second component of LLMs, which is tokens. The inputs to an LLM are tokens, and even the outputs are token. Token is basically a mathematical representation of the words. Now, it will be difficult to explain that over the board here. So let me take you to the laptop, and we'll see what tokens are. Now let's look at tokens. What we'll do is, we'll go to a browser and look for OpenAI tokenizer. The first link here, platform.openai.com/tokenizer, is where we are going. You don't need to log in to access this page. Now, let's type in some text here. This is a cat. So what it says is, it has 5 tokens and 14 characters. And if you count the number of words, it is 1, 2, 3, 4, and a full stop. And here, if you see the different colors, they denote that is the boundary of these tokens. Looking at this, it seems very simple that every word is a token, but it's not. So we'll see shortly. Let me add something more to this. This cat belongs to Lake Satyam. So now we added these things, this another sentence, and now what you see is belongs, it still is one token, to is one token, Lake, it has been split into 3 different tokens. Satyam has been split into 3 different tokens. You see 3 different colors here, right? So what I wanted to show is words will not always be tokens. There can be sub words that becomes a token. Now the thing is, you see that it is a grouping of, or a sequence of characters. That is the textual format that we were showing, but actually these tokens are something like this. So this text has been converted into this token. What you see is numbers, a matrix of numbers. Here you see a single dimensional array, but in reality a multi-dimensional structure exists, and that is how that gets stored in the vector database. Why do we do this? This is because the machines learn, or machines can understand numbers much better than the words. Now let me show you an example of how this size starts growing. So I clicked on show example, and it took an example here, right? And that got converted into numbers here. So whatever you type here, that will get converted into tokens, and you can see those tokens here. When you will be programming, different programming languages have different tokenizers, and you will have to use those tokenizers. So whenever you are sending something to an LLM, you have to convert it into tokens first and then send it. And again, the LLM will return tokens that you will have to convert into these strings. Now, why do we do this? Why do we convert it into these numbers, these tokens? What happens is, in case of machine, when it is learning, terabytes and petabytes of data, and it has to predict. So LLMs work in the way of predicting the next word, and that is how they complete the sentence, and then paragraphs and pages and so on. Now, how to predict the next best word, that data must be organized very well. When we are converting, converting these into tokens and storing it, what we store is called embeddings. Again, I'll be creating another video on that. But yeah, those are the embeddings, and those embeddings get stored in the database, which is called vector database. Vector because it is a vector, and it will be a multi-dimensional vector. And in that vector, 2 things that are very similar, say cat and kitten, will be close to each other, and it has a complex mathematical calculation as to how it predicts the next word. I will cover a little bit of that in one of the later chapters, but for now, just look at this is what tokens are. Now let's move on to the third component of LLMs, which is context window. You all must have used ChatGPT. So the more context you give ChatGPT through the prompt, the better responses you get, right? So in this, how many words or how many tokens your model can take is the context window, because that is the window in which you can set the context. more context you give, the richer response you get. For GPT-3, the window size or the context window size was approximately 2K tokens. 2K tokens is roughly like 1500 words, which is like 5 to 7 pages of document, a dense document. With 3.5 GPT 3.5, that context window got doubled to 4K, which is something like 3000 characters and 10 to 14 pages. In 4, that again got doubled to 8K, which is like roughly 6000 characters, 20, 25, or somewhere around 30 pages of documents is what you can feed as context in one prompt. And then the GPT-4 Turbo, that has a context window of 128K. 128K, that's massive, like 100K words, which is like a 500-page book. So you can pass an entire 500 pages book in one context window to GPT-4 Turbo. So just imagine the kind of data it can take in, process, and give back the responses. So that was about the context window. With that, we are left with the last component, and that is the architecture, and we'll touch upon the transformer architecture. So let's go back to the board. And the last thing that we want to discuss in this LLM is the architecture, the transformer architecture. We're not discussing about any other architectures. And in fact, for the product managers, you don't really need to understand the architecture, but a very high level view of how it works, right? So I'm not going to go into the actual architecture. I'll take an example, an analogy, and try to explain how the transformer architecture works. Now, if you have already gone through the architecture, you understand it, then you should be skipping this part. This is not going to be accurate. This is just going to be a very high level way of understanding if you do not know how transformer architecture works. So that's a disclaimer. Now, let's say that there are a few friends sitting in a room. They know a part of the story, no one knows the whole story, and they have to work together and predict the story. And that is how the transformer architectures work. Okay, so so there are multiple friends. They're all sitting here. This friend is Siddha. This is, say, Matt, Sat, Cat, the, on. So these are different friends. And what they're going to do is they are trying to work together and form the story. So the first concept that comes in there is self attention. And you might have heard this whole transformer model that came in as a paper, and it said the title of that was "Attention is all you need." Now, what is self attention? Self attention is each of these friends sitting here. They will, listen to all the other friends. Now, let me try to write it down. What that means? That means the is going to listen to Matt. So the and Matt come together. Similarly, the and Sat, the and Cat, the and the. Not sure if it is visible. the and on. Right? Similarly, Matt is also going to listen to all the other friends. So he's also going to pay attention, or she's also going to pay attention to all the other friends. What that means is it becomes Matt, the, Matt sat, Matt cat, Matt the, and Matt on. Similarly, you will be doing it for each of these friends listening to each other, and that is the self attention. I'm not going to fill this hole and take so much of your time, but you understand what I'm trying to do, right? Or let me pick one more. So cat the, cat Matt, cat sat, cat the, cat on. Right. After this, when it goes to the next layer, what happens is, you know, just look at this. The mat. It looks, yes, this can be part of a sentence. The sat, no. The cat, yes. The, no. The on, no. Mat the, mat sat, mat cat, mat the, mat on. Mat on might be. Similarly, cat the, cat mat, cat sat, yes. Cat the, cat on might be, yes. So all the important, or whatever are the possible combinations that remain, and the rest is, and those are passed on to the next layer. So what will happen is, when you go to the next layer, and actually let me do that here. I'll not write everything to save time. Sat the, sat mat, sat cat, sat the, sat on. So sat on looks something possible. I'll just write that one. I'll skip all the others. Cat, we've done the mat, the mat. Okay. The sat, the cat, we have already done it, so I'll skip that also. The on, it doesn't make sense. So the mat is something we picked on. Now on the, yes, that makes sense. On the, on mat, okay. On mat, on sat, on cat, okay. On cat, on the, yes, and we have already written that, so we'll skip that. So all these are the important ones. What I'll do is I will rub off all the ones that are, that doesn't make sense, right? So I'll remove this, I'll remove this, sat on, cat the, cat mat, cat sat, cat the, cat on. Okay, so we have these many valid kind of combinations. Now what will happen is all this will come on this kind of axis, and now we'll predict that, okay, the cat on mat, or the cat sat on the mat, right? So those kind of things. So in the next layer, again, each of, now these become those friends that we were talking of, and these friends will again you know do that self attention. But now, since there are multiple heads in one circle, this is called multi head attention. Similar thing, but yeah, you get the concept, right? So in that part, what happens is, So you see how the story is now being formed, right? With all these random words. So what we are saying is the cat sat on the mat, right? So this looks like a sentence or a story, as in my example. Now, when you are forming, and you're not forming just this small sentence, say in GPT, you ask it to write an essay, it writes a complete paragraph, right? A complete story. So, this kind of thing will keep happening layer after layer. And when you pass from one layer to the next and to the next, that is called um, feed forward network. So in the network, you are feeding it forward. And then finally, at the final step, this thing will happen, that this will be predicted. And here we just picked up a finite number of words, but this is how the next word can be predicted as well. Okay, so with its knowledge base, it will be like, okay, what can be the next best word, and it will predict that and it will use that. And then the final step is to compile all this and put it together and output that. So kind of that is what that is how these transformer architectures work. Again, this is very, very abstract, and if you really want to understand the architecture, um, you can mention that in the comment, and I can make a video on that. Now, one thing that you have to be aware is these prediction of the next words that are happening, or these kind of assembly that is happening, that is based on the probability. Say for example, um, uh, the neural network starts with something, or we give it an input and it starts with say the dog, or the dog slept. Now, what could be the next word? I think on can be the next word, right? What will be the next word? The. Now, the next word, it's like, based on its knowledge, how the language is kind of constructed, it keeps on adding that next word. But now here, it can be couch, it can be lap, it can be its dog bed. Right? So now, based on the probability, it will pick up one of this. Now when it is all based on probability and statistics, that this model picks up the next word. Now that word can be incorrect in your context, and that is when you might feel that the model is not giving me the right answer, or it is hallucinating. But there's one thing I would like to say here. Number one, the hallucinations have gone down drastically. But is it that the machine cannot hallucinate? No, that's not correct. It can. But think of it as a human being. So a child listens to their mom, dad, and everyone living around them. We're not explicitly teaching them, but they pick up words, then they pick up sentences, and they start speaking. They start doing all the stuff. Similarly, the machines are doing that now. Now, does a child not make mistake? Yes, they do. Similarly, the machines, can they make mistake? Yes. Now, the other thing is, when you are asking something to an LLM, it knows a lot of things and it can generate a lot of things, but it all depends on how you ask it to do. And that is why you have to set the context You have to guide it so that it gives you the kind of answer that you want. Every question can have n different interpretations and n different responses that the user or the viewer will say, yes, this is the correct thing. But that will depend on the context. So it is very important, even as product managers, that you understand how to write prompts. That is, how to talk to these machines. If you're talking to a person who understands only English and you start asking question in some other language like French, they will not understand, right? So it is very important, and perhaps that is one of the most important skills for today: prompt engineering. And my next video will be on prompt engineering. See you soon. Till then, thank you and goodbye.